Hello everyone, let's solve some LeetCode today. So today we have this LeetCode 207 course schedule problem. Now in this problem we will be having a few courses and we have to figure out whether we can take all the courses or not. Now each of these courses are actually dependent on other courses also. So for example, if you have a course A and then a course B, then it is said in the question that you can only do course A if you first of all do course B. It means you have to go from B to A. Okay, so here you can see that there is some kind of edge or some kind of a relationship between the two things. So till now we can make a guess that this is actually a graph problem here. So it means that each course is actually a node and this prerequisite array actually stores all the edges between the nodes. Let's take a simple example to understand how this will work. So here we have a few courses from 1 to 6. Now here the course number 2 depends on course number 1. It means until unless I do course number 1, I cannot do course number 2. Okay, that's why we have an edge from 1 to 2. Similarly, the course 3 depends on course 2. That's why we have an edge from 2 to 3. And in the same way, the 4 depends on 3, and then the 5 depends on 4, and 6 depends on 4. So the 6 and 5 courses cannot be done until we do the 4 course. So basically, we have to figure out whether we can actually perform all these courses or not. So yes, we can. If we start from 1, then first we complete the first course, then we go to the 2, then we complete it, then we go to the 3, then we complete this one also, then we go to the 4, we complete this one, then we go to the 5, or we can go to the 6. We can go to any of these two courses because they depend on 4. So you can either go to 5 or you can go to 6 from 4. So first, let's just say I go to 5, I complete this, then I can also complete the 6 also by going back to 4 and then just going this way. So in this way, I can see that first I need to do first course, then second, then third, then fourth, then we can do 5 and 6, or we can do something like this: 1, 2, 3, 4, 6 and 5, because this order, okay, the 6 and 5 depend on 4, they don't depend on each other, correct? So we can see that there is some kind of ordering in which we will have to do the things, right? It is called topological sort. Basically we are sorting these nodes based on the edges. So these edges will define what kind of ordering or sorting we will have at the end. Now here is another example in which we cannot take all the courses, and let us see why. So first we will complete this course, okay, because this does not have any dependencies. It is actually a dependency for others, but it does not have any incoming nodes, so it does not depend on anyone. We can complete this course by itself. Now we go to 2. Now 2 depends on 1, okay, so 2 depends on 1, but as you can see that 2 also depends on 6, right? So we need to complete first and sixth course before we can complete the second course, right? We have already completed the first course. Now let's just try to complete the sixth course. Okay, so I try to complete the sixth course, but the sixth course depends on fourth course, right? So I need to complete fourth course first, and then only I can complete the sixth course, and then I can complete the second course, correct? But the fourth course also depends on this third course. So I need to complete the third course, then only I can complete the fourth course, then only sixth course, and then only second course can be completed. But here is the catch. The third course itself depends on the two course. So I need to complete the two first, then only three will be completed, then only four will be completed, then only we can complete the sixth, and then only we can again try to complete the second. But as you can see that second cannot be completed as of now because it anyways depends on the sixth. So this is where you can see why we cannot actually take all the courses at this point, because this two actually depends on two courses that in turn depend on other courses, which again depend on the exact original course too. So we are basically creating a cycle of courses, and because of this cycle we are not able to actually complete any course in this cycle. And of course we cannot complete the fifth course also because we need to complete the fourth course. Fourth can only be completed once we complete the second course and third course. So yeah, after this first course we cannot actually take any other course. So this is basically the whole premise of this question. As long as we detect a cycle in our graph, we know that we cannot complete all the courses or take all the courses, and we simply return false as answer in our code. Now, one thing to note is that in this question, we are dealing with directed acyclic graphs. In these kind of graphs, there is no two-way edges. Okay, for example, in a normal graph, something like this: 1, 2, 3, then 4. These edges means that there is an edge between 2 to 3 and also a 3 to 2. So these edges are two-way communication. But in directed acyclic graphs, there is a directed edge. So for example, if I have one and two nodes, then I can see that okay, there is an edge from one to two, but there is no edge from 2 to 1. This does not exist. That's why we are using an arrow. Because if we actually had an edge from 2 to 1, then there will already be a cycle at each edge. And that's why we will not be able to take pretty much any course, right? That's why we are dealing with DAGs in this question. And this topological sorting also works for DAGs only because directed acyclic graphs does not have a cycle. That is why we are able to actually properly create this entire ordering. So basically in this question, we just have to figure out whether the given graph is a DAG or not. As long as it is a directed acyclic graph, we can complete all the courses. We will simply return true if it contains some cycle. For example, we can have a graph like this, and then again from 3 to 1, there is a cycle. Now this is a directed graph. Okay, each edge is actually going one way or the other way. Okay, so there is no two-way communication. Each edge is in a particular direction. But even after that, here we are actually getting a cycle from 3 to 1. So it is actually a cyclic graph. And so for a cyclic graph, there will be no valid topological sort. So how do we actually figure out whether there is a cycle in our graph or not? Because we know that as long as there is no cycle in the graph, we can take all the courses. So there are actually two ways to do this. First is definitely DFS, and then we have a BFS. So we'll have to track the path visited and visited arrays in DFS. In terms of BFS, we will have to figure out a topological sort, or you can say topo sort. As long as this topological sort exists, then we know that there is no cycle in the graph and we can simply return true. If it is not a valid topological sort, we know that we can simply return false because it will have a cycle for sure. Now, both of these solutions are great and will use pretty much the same time and space complexity, but we are going to go with this particular solution. Now, if you don't know what is topological sort, you can check out my other videos. So here we have a cycle in our graph, so we will know that, okay, we cannot create a proper or valid topological sort. Now, how are we going to figure out whether this cycle exists in the graph or not with the help of topological sort and BFS? We will simply use Kahn's algorithm. So we will basically have to keep track of two things. That is, first of all, in degree and Q for BFS. Now, in degree simply means how many edges are coming to a particular node. For example, in this first node, we have how many edges incoming? 0. So it means the in degree for this particular node is 0. Similarly, for 2, we have an in degree of 2. Then similarly, for 3, we have an in degree of 1. Why? Because only one edge is coming from 2 to 3. For 4 also, we have only single edge coming to it. So we can say its in degree is 1. And for 5, we have 1 as in degree. For 6 also, we have only 1 as in degree. In degree means how many are coming in. Okay, so only 1 is coming into 6, 1 is going out. So that is out of degree. That's not part of in degree. So we will have indexes like this 0, 1, 2. Since the arrays are 0 bits, so we will initialize an n plus 1 array here. Now 0 node does not exist. So the in degrees of 0 will be 0. The 1 node exists and the current in degree is 0. The 2 node exists, the in degree is 2. For 3, the in degree is 1. For 4 also it is 1. 5 also 1. 6 also 1. So it seems that we don't actually need this 7th index. Now here we have in degrees for each and every node in the graph. First of all, we will have a queue, right? And in that queue, we will make sure to put all the elements with 0 in degree in that queue first. So I will put the 0 element which does not actually exist in the graph, and that's why it also does not have any out degrees, but we will actually handle it very easily soon. Also, we will have to put the first node because it also have a in degree of 0. So we will have these in a queue, and now we can actually start BFS. So BFS, and it will only run until unless we have something in the queue. Now in the BFS, first of all, what we will do is we will pop the element. Now then we can check in our adjacency list whether E exists or not. This particular popped element exists or not. If it does not exist, we simply continue. So if E does not exist, we simply continue. But what if E exists in our adjacency list? It means that it exists in our graph also. So we will have another answer array or basically a topo array. So in the topo array, we will have topological sorting. So here at this point, if E exists, we will say topo dot append E. So basically when we will have element as 0, we will continue from here. So this will be gone and will also not be added in the topo. But for first element, we know that it exists. So this line will execute and we will have 1 in the topo. Now, after adding the element in the topological sort, what we have to do is, first of all, we know that we have removed the one, okay? So this process is like removing these particular edges. So if I remove this one, what is the in degree of 2? Now, at this point, only one edge is coming to the 2. So in degree will become 1, right? That's what it should become. What we will do is basically we will reduce the in degrees for each and every node that was connected with 1. Okay, so for 1, the only connected node was 2. So we will have to reduce the in degree of 2. But how do we do this, right? Well, what we will do is we will have to run a for loop. So we will run a for loop on the adjacency list for this particular element E that is currently being processed. And all the nodes that are connected with this E element, well, we will actually reduce their in degree. So what I will do now is in degree minus equals 1. So here I'm basically reducing the in degree of all these nodes by 1. And suppose that somehow after reducing the in degree, it actually becomes 0. So the in degree of this particular node becomes 0. I will have an if statement. So if in degree of this particular node becomes 0 after this, what we will do is we will simply add this to our queue. Simple Khan's algorithm, right? So queue dot append this particular node. And then eventually we will actually run BFS on this particular node also because it is in queue. So this is how it will keep on working. But if you notice properly here, once the first node is processed, we see that there are no nodes for which the in degree will become 0. For 2, the in degree is 1. For 6, the in degree is 1. For 3, it is 1, 1. And for 5 also 1. So it means that there are no particular nodes in this graph anymore for which the in degree is 0. It means we cannot actually proceed with the topological sorting after this. This particular BFS will simply end just after processing the first node, and then in our topo sort we will only have first node. But we know that for a topological ordering to be valid, the topological ordering must contain each and every node of this particular graph, which means at the end I can check if len topo double is equals to n. And let me just make a division here so that we will not confuse. So if at the end length of the topo array is basically same as n is number of courses. So if the topological sort array contains n nodes or n elements, we know that there are no cycles in the directed acyclic graph, and that's why we were able to get a proper ordering. So we can simply return true. Otherwise, if the topo sort is actually less than and we know that we found a cycle, and that's why we had to stop the BFS in the middle of creating this topological sort. And so we know that we can simply return false. It means that we cannot actually go through all the courses because there is a cycle. So this is how you actually solve this particular problem. You simply use Khan's algorithm to get this topological sorting, and at the end you check if this particular topological sorting is valid or not. If it's not valid, you know that there is cycle in this particular directed graph, and you can simply return false. Otherwise, if it's valid, we can simply return true. Let's go through the code now. First of all, we are creating an adjacency list. The size of this list will be number of courses. Simple, right? And now for each course, we have a set, and this set will contain how many other nodes are dependent on this one. We have an in degree array also, and this will be simply the size of the number of courses also, because for each node we need to figure out the in degree of that node. Now here we are basically populating our adjacency list and our in degree. We have a prerequisite array here, and this will contain all the edges. So for each edge in the prerequisite array, so the edge will look something like this: 1, 2. Now understand that in the question we have already been told that you have to complete 2 before 1. 1 actually depends on 2. It means that the edge is from 2 to 1. And so basically they have given the edge in the reverse order, and we have to basically figure out that okay, this is how it will be. And so once we get the edge, we have indexes 0 and 1. So we know that we have to store this particular element for this particular element. So that's what we are doing here. In the adjacency list, we are basically storing the 0th index of edge for the first index of edge. It means we are storing the 1 node for 2 because there is an arrow from 2 to 1, as we already see. Now similarly, we are also setting the in degree within this for loop. So we are saying that the 0th element of edge will have an in degree from first element, as we saw here. The 0th element or the first element actually have an in degree or incoming arrow from 2. So that's what we are storing. And then what we are doing is we are basically placing all the nodes in this queue that actually have the in degree 0. Now we are declaring the topo array that will contain the topological sort, and we are starting our BFS traversal. So while we have some element in the queue, we will keep on running this loop. So first we will pop the element, append this element in the topo sort, sort, and then we will actually go through all the connected node of this particular element. So we will use adjacency list. So what we are doing is that we are taking the list of all the connected elements to this particular element from the adjacency list, and we are going through them one by one. So first we do is we reduce their in degree by 1, and then we check if their in degree is now 0. So we can append that node into the queue, and then we can go through that node in the next iteration of this while loop. Now once this entire BFS traversal runs, we have to check whether the topological sorting we found is actually valid or not. So we check the length of this topological sorting with the number of courses, and if it is less or not equal, we know that there is a cycle, so we simply return false. Otherwise, we know that all the nodes have been traversed, we have a valid topological sorting, and so we simply say that okay, return true. Now in the code we did not actually put this particular e does not exist check. And the reason for that is because of these constraints. So here in the constraint, you can see that the value of A and B can from 0 to the number of courses. So we did not actually need to put it here because 0 can also be a valid node. Also here you can see in the constraint that the pairs of prerequisites I are unique. It means that the edges are unique, and this is the reason we were able to use that here. Otherwise we would actually had to use a hash map. So yeah, let's run it and see what happens. And here we can see it is taking 7 milliseconds and it's pretty efficient solution. Here both time and space complexities are v plus e. V is the number of nodes and E is the number of edges. The reason for this time complexity is BFS, and it takes V plus E. The space complexity is the same because we are using adjacency list. So adjacency list actually takes V plus E space complexity. So if you have a question that you would like me to target, then let me know in the comments. Bye.